Hey, and welcome back. This third and final lesson in Chapter 6 is about two new distributions called the binomial and the geometric distribution. And they come from the binomial and geometric random variables. So we first had to explore the idea of random variables, which we've done now. Now this distribution will be added to the other distribution that we've known, which is called the normal distribution. So there are three main distributions you need to know in AP statistics: the normal distribution, the binomial distribution, and the geometric random distribution. Okay, so to start with, we're going to talk about what creates what's called the binomial setting. So again, bi means two, and binomial is two terms. So the binomial setting happens when you have something that takes on these following four characteristics. First off, the random variable has to be binary. That means each thing that occurs has to be able to be determined as a success or a failure. So such as flipping a coin, heads could be success and tails could be failure. Rolling a dice, if you roll the number 5, that would be a success. And if you don't get a 5, that could be a failure. Shooting a basketball, if you make it a success, if you miss it, a failure. So binary meaning two different outcomes. Secondly, independent. Each specific trial has to be independent of the other one, which actually ends up dealing with our last S here. So we have independent, and the last S is success. On each trial, the probability of success must stay the same. So if the events are independent, it's likely that the probability of success will stay the same. So those two go generally hand in hand. It's the third one we have to focus on, because the third one is what will differentiate between the binomial and the geometric setting. The third one is the successes. So what we're interested in the binomial setting is the number of successes that you get in a specified number of trials. So for instance, if I shoot 10 free throws, the number of free throws I make, okay, what's the probability I make 6 out of 10? That's a binomial setting. Okay. Now, I'm going to jump down all the way and discuss the geometric setting so we can compare and contrast these two different settings. So here's the geometric setting. And what you're seeing here is that the first, the second, and the third descriptor here, okay, the traits are the same. Okay? So we still need to be binary, success or failure. We still need independence, meaning the probability of success stays the same. So there's the I and the S. But the third one, T, is different. So now, instead of looking at the number of successes in a fixed number of trials, we're looking at how many trials until we get our first success. Meaning, instead of how many do I make in 10 shots, we say, how many shots do I have to shoot before I make one? Okay. How many times do I have to shoot a free throw until I make one? How many times do I have to flip a coin until I get a heads? How many times do I have to roll a die until I get the number 5 to show up? This would be a geometric setting. Okay. And part of the reason it's a geometric setting, if you've explored arithmetic and geometric sequences, is because in a geometric sequence, it's a repeated multiplication, and that's what's actually going on in the geometric setting, and we'll get to that. Okay, so those are the two different settings, the binomial setting and the geometric setting. Those are the distributions we're going to explore. Now, here are the ideas: binary, independent, success, and successes. Okay. So the binomial random variable, okay, has a specific discrete distribution. So it's a discrete probability distribution because there's a specific number of specific number of successes and a fixed number of trials. So if you shoot 10 times, you can make anywhere from 0 to 10 shots. Okay. As an example, this is showing X is each child, a particular pair of parents, has a probability of 0.25 having type O blood. So this is talking about what percentage chance you have a specific blood type. And if these particular parents had 5 children, what is the probability that 0, 1, 2, 3, 4, 5 of them have type O blood? So this shows you the different sort of combinations, and we're going to focus on some other examples. Now, what we want to look at is this idea. So what I'm going to do is we're going to explore this idea of the binomial coefficient. Now, what this means is, let's say we roll a die, okay, and you can get a 5, or you don't get a 5. The probability of getting a 5 is 1 out of 6. The probability of not getting a 5 is 5 out of 6. Okay. Now, if I roll a die again, I could get a 5 or not. If I roll again, I could get a 5 or not. And again, and again, and again, and again. So I'm going to kind of work this out a little bit so we can explore the idea. So this is if you roll it 3 times. Now, in the binomial distribution, what we're interested in, because this is a random variable, is how many 5s you get. Well, you could get 0, 1, 2, or 3 5s. If you roll a die 3 times. The most 5s you can get is 3, and the least 5s you get is 0. So this is x, that's the number of 5s you get, and this would be the probability of x. Now, we think, well, maybe the probability of getting x is not that bad. Okay? So how do I get no 5s? Well, to get this one right here, I would do 5/6. That's probably I don't get a 5. To the 3rd power. I would have to repeatedly not roll a 5. And I'll show you that right here. So not a 5, not a 5, and not a 5. So that's here. 5/6 to the 3rd power. Now, how about if I want to find the probability of getting all 5s? Well, that's 1/6 to the 3rd power. Okay. Why? Because that's going to take place up here. So there's 1, 2, 3 5s. So 1/6. Oops, hello. I'm too high. 1/6 to the 3rd power. That's a 6, and that's a 3. Okay. Now, those aren't bad, but it gets a little harder when you get in the middle here. So if I want to get exactly 1 5, we'd say, well, I want 1 5, and I want 2 of them to not be 5s. So this to the 1st and this to the 2nd. That's mostly right, but it leaves out an important idea. So we do want 1 5, and then we do want 2 that are not 5s. But what we're calculating here is a probability to get a 5, and then a not 5, and then a not 5. But it's also possible you could get a not 5, then a 5, and then not a 5. It's also possible you get 2 rolls that are not 5s, followed by the 5. So this here are the combinations in which you can get exactly 1 5 in 3 rolls. There are 3 different ways in which this can occur. And you'll see that if you go into this chart up here. So I'll make this a different color now. So if I want to get exactly 1 5, well, what could happen is I could go here, and then here, and then here. So that's 1 5. Or I could go here, and then here, and then here. So that path also has exactly 1 5. Or I could go here, not 5, and then another 5. There are 3 different paths that lead to you getting exactly 1 5. And to get this number, we don't want to always have to make this sort of table here, or make a whole tree diagram. That would be really hard. What we want to do to get this number, which is 3, is we want to do something called the binomial coefficient. So that would be 3 choose 1, which can also sometimes be written as this, 3C1. Okay. So this is the number of combinations. So the number of combinations, sometimes you see this like taught with the idea of permutations, is the number of ways in which these things can occur, in which order doesn't matter, because we know it doesn't matter which way the ends occur. So combinations is figured out by doing 3 factorial over 3 minus 1 factorial times 1 factorial. Okay. So this number, factorial, on the top, and then the subtraction of the 2 numbers, factorial on the bottom, and then the second number, the number of combinations we want, factorial on the bottom. So this is called the binomial coefficient. And in this particular example, you would have gotten a 1 here, a 3 here. This next example would have given you a 3, so this would be 3 times 1 to the 6th squared times 5 to the 6th, 5/6 to the 1st, and this would be 1. So it's 1, 3, 3, 1. Those are the number of combinations in this particular way. And you can see that in this chart. There's one that's kind of this all sort of coral color. There's 3 pinks, and if I did the other path, there would be 3 more that haven't been shaded in, and then there's 1 yellow. So 1, 3, 3, 1. And just to connect this to another idea you may have seen, this also comes from this idea. Some of you may have seen this. Okay. And there's the row we just got. 1, 4, 6, 4, 1. So this is called Pascal's triangle. And Pascal's triangle actually shows us the combinations. The one we just did was this one. Okay? So if you flip a coin 3 times, those are the different number of combinations of 0, 1, 2, and 3 heads. Flip a coin 5 times. Okay? Then what would happen here is this is the number of combinations of 0, 1, 2, 3, 4, and 5 heads. Okay, so it's most likely flip a coin 5 times. There's 10 different ways in which you can get 2 or 3 heads. And most likely you'll get 2 or 3 heads. You might get 1, you might get none, you might get 4, you might get 5, but those are less likely. So this is the idea of the binomial coefficient and how many combinations there are. Now that becomes important because that's what we're going to be doing in this particular section. Oops. So that's this idea here, that binomial coefficient. And you can see the formula here. So n choose k, or n things taken in combination k at a time. N factorial over k factorial, n minus k factorial. And this then goes into this formula, which is what we were exploring the last time. So if you think about this, if I say how many ways can I get the number 5, to roll a 5 twice, okay? Well, it was 3 choose 2, and it was 1/6 squared times 1 minus 1/6, which is 5/6 to the first. Okay. Now, you can use this to calculate the probability of getting a specified number of occurrences in a binomial situation. So if I say I'm shooting 10 free throws, I'm an 80% free throw shooter, I'll probably make 8 of them. I could use that idea. So if I explore that, so that's a binomial setting with 10 trials and a probability of success of 0.8. And this is x. And I say, what's the probability that x is equal to 6? What's the probability that someone makes 6? This would be 10 choose 6. Okay. And there's an 8% chance you make it. You want to make 6. There's a 20% chance you miss it, and you're going to miss 4. You figure that out, and you get the likelihood of getting exactly 6 successes. Now, there's another way to do it, which I'd like to share with you. You can also use your calculator. Now, this is the binomial setting. And what we learned, and this is called the binomial distribution, is there's a normal distribution function. There's also the binomial. So if you go into here and you go to statistics, menu statistics, there's a distributions menu. And we explored the normal distribution in chapter 2. Now, if you scroll down, there's a binomial distribution. Now, if I want to find the probability of getting exactly 6, I can do a PDF. It says how many trials. I was shooting 10. I'm an 80% free throw shooter. I want to make 6. Hit enter. And that does the calculation for you. There's an 8.8% chance. Now, if I wanted to find the probability of getting 6 or more, I would do a CDF, which is cumulative density function. Again, I'm shooting 10. I have an 80% chance of success. I want 6 or more, so 6 to 10. And I would get 96.7%. Okay, so that's the binomial CDF and PDF function in your calculator for calculating probabilities in the binomial distribution. No. Hi, I wanted to show you how to do that same process on the ClassCalc calculator. So to do a binomial distribution, you go into your graphing calculator, you go to stat, which is where we spent most of our time. And then you go to distributions, which is the same place the normal distribution was. And you see binomial distribution was in here. And we'll put in 10 because that's how many trials I had before. I said the probability of success was 0.8. So let's say you're an 80% free throw shooter. And the nice thing about the ClassCalc calculator is then it gives you a graph and you can hit that magnifying glass and you can see this is what that binomial distribution looks like. So you can see it's real likely that you're going to make 8 of 10, but you might make 9 or 7 or 10 or 6 or even 5 or 4. It's real unlikely to make less than 4. And then if we want to find out any of the probabilities, let's say we want to find out the probability of make 6, the probability of make 6 to 10. I like the CDF function. So you can put in 6 to 6, and that would be the probability you make exactly 6, which is 0.08808, which is what we got on the TI Inspire calculator. Or if you want to go 6 to 10, we can put in 6 to 10. And not only does it tell you the probability of 96.7% or 0.967, it also shows you graphically what it looks like. So that's how you do that on this particular calculator. Okay, now let's go back, not there, to our notes. Besides calculating the probabilities of specific values in the binomial distribution, it's also important to figure out how to find the mean and standard deviation. This will come up later in chapter 7 and 8 and 9, and we'll explore this idea in great detail. Okay. But to calculate this, we can do a weighted mean like we did before, but what we'll find is that these formulas will give us the mean and standard deviation. And the mean formula is one you would expect. So if I say I'm going to shoot 10 free throws and I'm an 80% shooter, I say, how many do you expect me to make? How many on average will I make? You would probably say 8. 10 times 0.8. And that's exactly correct. You do n times p, and that gives you your mean. Standard deviation formula is not quite as straightforward, but it can be proven. Okay? The standard deviation formula is the square root of n times p times 1 minus p. Now, I'll show you that these are available to you on the formula sheet. Okay. So if you go in here and you look at our distributions and formulas, you'll notice that these formulas are here. All three of the ones that I just shared with you. The figuring out a specific value in the binomial setting is that first one. Okay. The mean and the standard deviation formula are available to you on the formula sheet that you get on the quizzes, the tests, and the AP exam. All right. Now, this is an example of calculating the mean and standard deviation, which I'll allow you to work through on your own. All right, a couple of big ideas, which is really a preview of chapters to come. If you are sampling without replacement, again, remember what we're doing here in this idea of random variables is we're combining these random phenomena. Now, if you're sampling without replacement, it's really not independent, right? Because if you're taking cards out of a deck of cards, the probability of getting a hard changes every time you draw a card out. However, in statistics, what we do is we say, well, things are generally independent or close enough to independent as long as the sample size is less than 10% of the population, less than or equal to 10% of the population. So if you have 1,000 people in your population and you sample 100 or less of them, we will say, well, that's generally close enough to be independent. It's it's relatively independent. So we will allow statistics will allow us to do the formulas that require independence in this setting. Okay, so that's called the independence rule. Okay, so it's virtually independent. It's not perfectly independent, it's virtually independent. And then the last thing is we're going to explore this idea of normality. Now, in a binomial setting, if you look at someone who's an 80% free throw shooter, you expect them to make 8, but they might make 9 or 10 or 7 or 6 or 5 or 4. And this is actually the probability distribution of that, shown as a histogram. You can see you can approximate this histogram with the density curve. However, the density curve is skewed to the left. Now, if we shoot 20 times, we expect to make 16. And you might make 17 or 18 or 19, all the way to 20, and all the way down to 14 or 13. And again, you can approximate that, and it's getting to be fairly normal, but it's still a little bit skewed to the left. However, if we shoot 50, again, we expect to make 40, because 80% of 50 is 40. And you can see this density curve, or this histogram, is getting really, really normal looking. Now, there is a little bit of a tail on the left, but it's very, very small. So again, what we're going to say is this distribution is approximately normal. It's not normal, but it's approximately normal when you've met in a certain condition. That condition is that the number of successes that you expect, which in this case is 40, we expect to make 40, and the number of failures you expect, which in this case is 10, as long as both of those are greater than or equal to 10, we'll say it's approximately normal, okay? And that's this condition right here. So right there, kind of in the center, n times p and n times 1 minus p. So that's the number of successes you expect and the number of failures you expect. As long as both of them are greater than or equal to 10, we'll consider the distribution approximately normal. And if it is approximately normal, and you use these formulas for the mean and standard deviation, you can now calculate probabilities using the normal distribution and the normal CDF as an option. And that's an example here of how to do that. And we'll work more on that in your homework. Now, to try and finish up this video, we got to get through the geometric setting. So we talked about this. The difference here is we're not looking at how many free throws you make in 10 shots or how many free throws you make in 20 shots. We're looking at how long until you make it. Okay? So that's called the geometric setting. And we have the geometric random variable. Now, the reason it's geometric is because, let's say in this case, it says the probability of success in this circumstance is 1/7. Okay? The probability of a correct guess is 1 out of 7. And so the probability to guess it right on the first time is 1/7. Probability to guess it right on the second time means that you guessed incorrectly on the first time and then you guessed correctly. So it's 6/7 times 1/7. Probably on the third time that you guess it right means the first and the second time you must have guessed incorrectly those 2 times. Then you guess correctly. So 6/7 times 6/7 times 1/7. And if we kept going, if I said, what's the probability to guess it right on the 8th time? Well, you'd have to fail 7 times in a row. So you just continually multiply by 6/7 to work this out. And that's why I said earlier it's related to the geometric sequence, because the geometric sequence is repeated multiplication. So what we're doing here is repeatedly multiplying by 6/7 as we want to go further and further out. Because every time you fail, you have another chance of 6/7 of being in failure here. So this is the formula for calculating a specified number of trials in a geometric setting. It's just the number of the probability of failure times 1 minus when you want to be successful times the probability of success. So if we want to be successful on the 5th time, that means we're failing 4 times, and then we're successful on the 5th one. And you can use that to calculate the whole probability distribution. Now, one thing that you can notice that you can't really calculate the whole distribution because it goes on forever. You could be unsuccessful for 1,000,000 times in a row, 2 million, 100 million, okay, 1 billion, 1 trillion. So it's actually an infinitely long distribution. But what you'll see is it's always skewed to the right. It always follows a pattern like this. You're most likely to be successful on the first trial. Even the probability of success is 1%. You have a 1% chance in the first trial. On the second trial, you have a 1% times a 99%, which is just less than 1%, right? Which is 0.99%. So it will go down as you go on. Now, the mean of a geometric setting is 1 over p. Which makes sense, and I'll show you why. If you think about the binomial setting, in which case mu of x was equal to n times p, the question we're asking in the geometric setting is, when will you get your first trial? So we're wondering, when will the mean equal 1? Okay. So the question is, when do we expect to have 1 success? So when is n times p equal to 1? So then if you solve this for n, we divide both sides by p, right? You get 1 over p equals n. So that's the expected number of trials in a geometric setting. It's 1 over p. Now, it's kind of a long video, but there's a lot to explore there. Now, last thing before I go is I do want to show you that we explored this idea of this binomial function in the calculator. There is also a geometric function. So we can use a geometric PDF. We say, okay, well, I have an 80% chance of making a free throw. What's the probability it takes me 3 to make one? I can do it this way. Now, this one's not as helpful for us a lot of times if we're doing a PDF, because you can also do, if I'm an 80% free throw shooter, what's the probability it takes me 3 before I make one? Well, that's just me missing 2 twice, okay, times me making it once. And it gives you the same thing. So you miss it twice and then you make it. However, if I ask for the geometric CDF, that would be probably helpful to use a calculator. So this question is, okay, I'm an 80% free throw shooter. What's the probability it takes me, let's say, 4 or more before I make it? Now, I can't actually put in infinity here, but I can put in a large number. So this is the probability it takes me 4 or more. So it's very, very likely I will make it in the first 3. Okay? Now I'm going to show you how to do that same geometric calculation on the ClassCalc calculator. Now this one is a little different because they coded it differently, and they're going to change this, but it's not going to come out until January. So again, though, we're going to statistics and we're going to distributions, and we're choosing the geometric distribution, which is this one. And again, the probability of success, we're still going with this 0.8 idea, that the person being an 80% free throw shooter. Now, if you zoom in on this graph, though, you can see that it actually starts at 0, which is not how the TI calculator starts, because 0, based on how we usually define it in our class, means that you would have made it before you even attempted one. But how this definition is using it, and both definitions are valid, it depends on how you define it, is the number of misses before your first success. So this means you didn't miss at all on your first success. So if the question asks something like, what's the probability it takes you 3 shots before you make it, that means you had 2 misses. So if I want to find the probability of that, I'd find the probability of 2 misses. Okay, so that's the probability that that you missed twice, which means you made it on the 3rd one. So it's a little bit tricky. You'll have to, if you're going to use the ClassCalc calculator, which is what I'm going to use. We're not going to talk about how many attempts it took you, but how many misses it was before you made it. How many misses, the number of misses, that's what you're going to put in. So if I say what's probably you made it on your 3rd attempt or beyond, that means what's probably you missed 2 times or more, and you can just put in 2 and put nothing up there, and that'll give you the 4% that we're actually looking for. So that's the slight difference. Again, in this calculator, again, you can still do the geometric distribution, which I like, and it's graphical, which I think is better. But the parameters you put in are not how many attempts, but how many misses before you made it the first time. So it's a slight different way of thinking about it. It just shifts everything over 1. So if I say what's probably it takes you 4 or more attempts, that's the probably what's probably it's 3 or more misses. So that would be this 3 or more misses. So that's how you do that. Okay, so a lot to explore there, a lot to unwrap. You may want to watch this video again. We explored the binomial and the geometric settings. We showed the calculator function to calculate both the PDF and CDF function of both of those. Again, PDF is when you want a specific number of trials or a specific number of successes. The CDF is you want a range. Okay? We talked about the binomial coefficient, which is this n things taken in combinations of k at a time. Talked about the mean and standard deviation of a binomial setting. Talked about how you can approximate it with the normal distribution as long as it's independent. So that means that it meets the 10% condition. So the sample size has to be less than or equal to 10% of the population. And if it's approximately normal, meaning that both the number of successes and the number of failures that you expect are at least 10. And then finally we went to the geometric setting. All right, a lot there. Good luck with that.